In this video, we will solve a typical problem, which is the parity bit problem using recurrent neural network. In this video, we will need a prerequisite, which is the previous video where the entire architecture of a vanilla RNN was captured and explained. And we will be using the concepts taken from that video over here to model this particular problem statement. So let's try to understand what is the problem statement in the first place. So we get a stream of input like this. So we are at 0, we then get 1, and then we get 0 and so on. So the output is supposed to be 1 when we have even number of zeros present with us and 0 otherwise. So let's see how it looks like. So initially there is a 0 and we don't have an even number of zeros present with us, so the output is going to be 0. Now the input is 1. As of now, we don't have the even number of zeros with us again. The output is going to be 0. Now the input is 0. We see there are two zeros available with us, this and this. So there are even number of zeros available. We write it as 1. Then there is a 0, and this makes the odd number of zeros available. The output is 0. Now the input is 1 again. Even with input being 1, there are still odd number of zeros available with us. The output is going to be 0. And again, if I put 0 over here, now we have even number of zeros, 4 zeros available. The output is going to be 1. The next state is 1. Still we have even number of zeros. The output is 1. Now this entire prediction, so this could be considered as an xt for us, and this is considered as an yt for us. So based on these predictions, we need to predict the next state corresponding to a given input. So this is how the entire input and output structure is supposed to look like. The link to the problem statement is again taken from Chegg and will be available in the description for you all. So also the PDF corresponding to this video will be available in the description. I will urge you to download it and keep it handy for better understanding. So let's proceed to the solution. So this is the input and output which we have just discussed. We model xt as the input at time t. This is time 1, this is time 2, 3, 4, 5, 6 and 7. So we assume xt as the input at time t and yt is the output at time step t. And consequently yt is 1 if yt minus 1 or the previous time step it was 1 and the current time step we have 1, then we can get yt as 1, which will mean that till previous time step we had even number of zeros and we added just 1 to it and we still have even number of zeros, then only yt will be 1. Or until the previous time step we had odd number of zeros and on the addition of xt, which is a 0, we get even number of zeros and the result is 1. Now we write it formally in this way. Yeah. So yt minus 1 being 1 will mean at time t minus 1 we have even number of zeros. We got a 0 at time t. Now we are at odd number of zeros, so yt will be 0. Now we are at even number of zeros. Let's say this is another scenario and we add 1 to it. We still have even number of zeros, so yt will be 1. Now yt minus 1 is 0 will mean that we had odd number of zeros. Xt we add as a 0. Now we are at even number of zeros. We come to 1. That's exactly what I have explained over here. And this is the odd number of zeros. We add 1 to it. We still are left with odd number of zeros. So broadly we get 4 possible cases out of it. But this all happens at time t when we have the information from time t minus 1. We haven't made an assumption as to how the initial starting state is going to look like. At time 0, we don't even have a number generated with us. We can be 0 or it can be 1. Y0 could be 0 or Y0 could be 1 because 0 is neither an odd or even integer. What we will do now is to create a state transition diagram to which I am coming to in a minute, and show that it doesn't matter whether y0 is taken as 0 or 1, we are going to get the same set of transitions when we start from the initial state. So let's suppose if we take y0 as 1, we will assume that initially we start with an even number of zeros, or if y0 is equal to 0, we assume that we start with odd number of zeros over here. We proceed further and define three states. State 0, which is the initial state, state 1 and state 2, which are the consequent states, and how it will work, I will come to it in a minute. And as of now, we start with y0 is equal to 1, which will mean that state 0 is even. Now, we can say that transitions are possible depending on the x1 value. Like we are already at we are already at y naught. We have the information from the previous step to proceed to the next step. Just will depend on what value x1 is getting so that we can know where exactly we need to go. Now, as of now, S0 is state 0, which is at 1. Now, and this will mean that at time 0, there are even number of zeros available with us. Now, if xt is 1 or x1 is 1, we will continue to have even number of zeros. But if x1 is 0 or xt is 0, we will move a step ahead to odd number of zeros. So S1 is the odd state, which will identify as a state associated with odd number of zeros. And now if the next iteration comes to be 1 over here, like if xt is 1, we will still have odd number of zeros, we will remain in the state. Now if I get an output as a 0, if xt is 0, when I am at state 1, I go to S2, which is the even state. This will mean that I have three states over here. S0 is the initial even state. We assume that we start with even number of zeros at one point of time, and then we move ahead and define that if we start with even number of zeros and we get a 1, we stay in the same state as shown over here. But if we get a 0, then we now have odd number of zeros, which will be modeled by state 1. And now on state 1, if we get 1 over here, we still have odd number of zeros. On attaining a 0, we move to state 2, which is symbolic of even number of zeros. Now, if we are at state 2, we have even number of zeros. Addition of 0 will push it back to the odd state, like S1. Now, if I add one more 1 to it, like if I add 1 to it, like if I am already at an even state, I am adding 1 to it, I will come back exactly at where I was previously. So we started with y naught being equal to 1, which will mean that there is an even state, which may have started at one point of time, but we didn't knew what is the value of x naught was at that point of time. We just have the information of y naught being equal to 1. Now at S2 point, if our now at S2 state, if the xt is 1, we will be pushed back to S0 from where we actually started with. So that's why three states are needed over here. We will also consider the case when the y0 is considered to be odd. We proceed further and model the case where y0 is 0, or we consider the state 0 to be odd. Now the definition will be just reversed. While I will show both the images next to each other, the images are going to be exactly the same. The transitions will remain the same, just the definition of states will differ. Like if I start at an odd state, I get 1, I still remain in the odd state. That's what is symbolized over here. Now if I start with an odd state, I get a 0, I will go to an even state. I get a 1 at even state, I remain in even. I get a 0 at even state, I go to an odd state. And in odd state, if I get again a 0, I go back to the even, and on attaining 1, we go back to the initial odd state which we had modeled previously. So over here, S0 and S2, which were initially the even states in this setup, are now the initial odd state and the odd state, and S1 is just the even state. So the initial state was actually needed. We could be thinking that we could solve the problem in just two states only, odd and even. Why do we need a separate state at all in the first place? It's just to make sure that the process restarts after few iterations from where it began from. And on the top of it, a lot of states are being dependent on each other based on the value of xt being taken. Hence, the initial state transition was very much necessary in this place to be modeled out separately. So we get the transition S0, S1 and S2. These are the transition, if you can say these are the transition states. Now we have to make a transition between three states and we can solve it with two hidden states. Now what does this mean? So this will mean that, let's suppose I have two genders, male and female. I can identify it in the form of a vector 1 or 0, right? So I have two states I am able to identify with a vector which could be taking either of the values. It could be either 1 or it could be 0. Likewise, if I have three states with us, S0, S1 and S2, I can uniquely represent each of them with values like this, 1 0, 1 1 or 0 0, like this. So this is what is mentioned over here. So yeah, we proceed further and we assume 0 0 as S0 and 0 1 as S1 and S2 is assigned the value 1 1. So the assignment is completely random. It's not that I specifically have to assign 0 0 to S0 and I can't assign any other values, but this is just a random assignment to make sure that each state is distinctly represented by a vector of 2 units, because that's how we will be able to uniquely identify S0, S1 and S2. I can also have identified S1 as 10 as well, but that's not needed. We already have assigned S1 as 01. We could have put 10 over here in S2 as well. That would be a separate design experiment which we would be doing. But as of now, we just have to make sure that the representation in the term of the vectors is unique for S0, S1 and S2. So that's what we did over here, 0 0 0 1 and 1 1. So all of them are uniquely identified. We will proceed further to draw a table showing how exactly the transition is happening over here. So initially we started with S0, which was 0 comma 0, and we had an input value as 0. And over here I will highly urge you to just keep the initial table from the question handy with you to be able to understand it in a better way. Now if I am at 0 0, I get xt over here, and for the sake of convenience I will paste the transition diagram as well. So yeah, we were at state 0 0, and then we get the value of xt as 0, and this is what happens. So if we are at state s0, so this was like s0 for us, and then a value of 0 is attained, then we move to state s1. This is what we have modeled over here. On moving to s1, the value of the state s1 was 0 1. So this is what we are writing over here. So this is the previous state hidden values, h1 t minus 1 and h2 t minus 1. We encounter xt. We just don't bother about yt as of now, but just follow what is happening on the basis of how xt is behaving. So based on 0 0, I put 0 to it. Then from s0, I make a transition to s1. So now we are at 0 1. Now the next step is we are at 0 1. So this is like S1 for us. Now we are at state 1. We provide an input 1. This is as per the input which is given to us in the question. Now if you are at state 1, you provide an input as 1, you are going to remain in state 1 only. So this is what the transition diagram shows. So we are still at state 1 only. So it will be 0 1. We proceed further and we go to 0 1 and we encounter a 0 over here. Now if I look in the diagram clearly, if I am state 1 and on encountering a 0, we go to S2, and S2 is represented by 1 comma 1. So this is exactly what we do. We write 1 comma 1. We proceed further. This is 1 comma 1 over here. We put it as S2, like we already have moved from S1 to S2. This is our next step, and we encounter a 0. Then we go back to S1, and the value of S1 is 0 comma 1. Now we proceed further with the value of 0 comma 1, and we encounter a 1. If we are at S1 and we encounter a 1, we stay in S1. I will urge you to just look into the transition diagram drawn over here for better understanding. And on doing so, we are able to get a relationship between h1 t minus 1 to h1 t. Like this is the previous hidden state to current hidden state. This is the previous hidden state for node 2 to current hidden state of node 2. So the hidden state previously was modeled with h1 t minus 1. After you get an input as xt, you get the hidden state as h1t and h2t. So the summary till now is like this. First of all, we have a problem of parity bit calculation, and this is the stream of input values given, and corresponding to that stream, we have the stream of output values calculated. Now, what we need to do initially is to find out the possible states, which was clearly found out first by understanding what the previous state is and how the current input is going to be. And on the basis of the previous state and current input, we were able to get the current output. Now we model that clearly using the three states possible, like what the assumption related to the first state, and the S1 and S2 being odd and even state respectively. So S0 could be either an odd state or an even state. We just proceeded with S0 being an odd state as of now because the transition diagram remains the same. The definition of state don't really matter because they are usually assigned to values like this, which we have done over here. Like we assumed S0 to be a vector of 0, 0 and S1 as 0, 1 and S2 as 1, 1. And the reason for assigning the vector is because we were able to uniquely identify three states which will be representing the entire transition from one state to another, like based on where we are at now or based on the current value of yt and the future value of xt, we will be able to tell what is the future value of yt plus 1 will be. So we were able to get three states out of it, and to uniquely identify three states we need a hidden node with two values, a hidden vector with two values. So hence we had to consider h1 and h2 over here, and based on the current nature of the hidden state and based on the previous nature of the hidden state and the current value of xt, we were able to find out the future value of ht using the transition diagram which is drawn over here. Now there is a thing, we are in this table only, we can establish a relationship between yt and h1t and h2t. So we can write yt in the linear terms of h1 and h2t. So in order to do that, we proceed in the following way. So we find out the unique combinations of h1, h2 and y, and these are all at time t. So we see that 0, 1 it will give 0, 1, 1 it is 1, 0, 0, 1, and how this relationship came, it's all coming from the table over here. So we saw that this first thing, this 0 and 1, if I pick up, I am getting as 0. The next is 0, 1 is again 0, which is repetitive. So we pick this relationship over here. Then we say that 1, 1 is giving the value as 1. We pick up this. This 0, 0, 1, this we have already included. So we ignore that. And we proceed further to get one another value, which is 1, or which is obtained on getting this 0, 0. This is h1, h2, and we are getting 1. Now we have a matrix X which is pretty much reduced to like three valued matrix, and then we proceed further with representing it in a logical way. So we say that if I just observe h1, h2 and y, if I just consider h1 and do the negation of h2, we will be able to get y. Like if it is 0 and I do the negation of h2, which is 1 minus 1, and add them, we are going to get 0. And we just take 1, we do the negation of h2, which is 0, and we do the intersection or we do the addition, we get 1. So we take 0, we have 1 minus 0, we do the addition, we get 1 over here. So we can say that yt would be represented in this way, but we have to establish it in the form of decision boundaries, like we did in the ANN video playlist. Over here we represent the entire function h1t, h2t plus 1, and we add a bias term to it, which is b, and write this function in the terms of h1t and h2t. We get a term b over here, we enter 1 and 1, h1t and h2t, we get 1 plus b, we get 1 plus b. Now let's see the corresponding values of y which are there. This is 0, this is 1 and 1. So a target of 0 is attained only when this linear function was less than 0, and this is all with respect to the part 1 and part 2 of ANN artificial neural network playlist, for which I will put the link in the description as well. So just to know how the bias term is attained, I will urge you to go over to the playlist and have a glance at it, and then start from here. So over here, the value of 0 is attained only when this term b is less than 0. Else, if 1 plus b is greater than 0, we will be having 1 anyways. So we select the threshold, which is helping us to identify the negative value properly. We select b less than 0. We select a very arbitrary term 0.5 or 0.5 with a negative sign, because this is apparently less than 0. We get the decision boundary as this. So h1t minus h2t, we had 1, we subtract 0.5 out of it, so we get 0.5. Now we proceed further to see how the transition is happening between the states h1 and h2. Now we created this table. This table helped us in finding the relationship between h1, h2 and y. Now we will proceed further to understand how the h terms are related to each other with different time frames. For that, we create another table over here. So first we consider the behavior of h1t. Now if we are at s0 and we encounter a 0 over here, right? So we are going to be pushed to 0 comma 1, and for the sake of simplicity I paste the diagram again over. So yeah, we were at state S0, which was 0 comma 0. We encounter a 0, we are pushed to state 1. And what is exactly state 1? State 1 is 0 comma 1. This is what S1 is. S2 is 1 comma 1, right? So we are pushed to state 1, which is 0 comma 1, and we just have to look into the first value, which is H1. We write 0 over here. Now if we are at S0, we encounter a 1, we remain in S0, and S0 is 0 comma 0, and the first value of S0 is 0. We write it over here. We are at S1, which is 0 comma 1. We encounter a 0 over here. We will be pushed to S2. The first value of S2 is 1. We write it over here. We are at S1, 0 comma 1. We encounter a 1. We will remain in S1. The first value of S1 is 0. We write it over here. Again, we are at S2, which is 1 comma 1. We encounter a 0. We will be pushed back to S1. The value of S1 is 0 comma 1. The first value of S1 is 0. We write it over here. Likewise, if we are at S2, which is 1 comma 1, we encounter a 1 over here, and we are pushed back to S0. The first value of S0 is 0, which we write it over here. Now we can kind of write the entire sequence, or the entire understanding from this table in this equation. This is how it is going to look like. We say that the current value, this is the h1t value, this is the h1t value which I am circling over here. This depends on the negation of the h1t value which was in the previous step, which is h1t minus 1, and the h2 value which was there in the previous step, which is h2t minus 1, and we negate the term 1 or we negate the term xt, which is represented by 1 minus xt, and add b to it. B is a small bias which we are adding to it. On solving further, this is what we are getting over here. Now to give a hint as to how these negations are coming into place, if we see the values over here, the 6 values over here, first of all, this is a very small subset of the problem which we are solving. In reality, we won't be doing calculations like this. But since this is a numerical problem which will help in understanding the RNN in a better way, so we will restrict to these 6 values and see what exactly is an outlier over here. This one is an outlier over here. Now, if I try to model this one, we will be automatically able to model the other values. Now, if I have to model one, I have three things: h1, h2, and 0. So I can't negate h2 because it has 1 over here. So I keep h2 as it is. I negate the 0 over here, which will become 1 again. and I negate the input over here, which will become 1 again, and then I make the other negations as per the values which are present in the other boxes. So on doing so, it's just a pure heuristic based calculation. We are able to arrive at this. Usually, if I have to solve it, then I usually take values 1 and -1 interchangeably, which are used as coefficients of h1t minus 1 and h2t minus 1. And based on how the different combinations of minus, plus, and minus behave between these three values, I take a call which one is fitting the best. And the bias term is obviously there, which we tune in the next step. So in the next step, what we do, that corresponding to different values which we have considered, like the 6 different values which we had in the table just above, we calculate the term which we proposed. So this is the term which we have proposed. These are the values which we are getting. And we observe that we are getting the value of 1 only when 3 minus v is greater than 0, right? So the entire term 3 minus v is greater than 0 is happening only when this h1t was 1 over here. So on doing so, we get a relationship that b should be less than or equal to 3. We select b as 2.5 only. On doing so, we get the entire activation function, or I should say the step activation function, looking like this. We have minus h1t minus 1 plus h2t minus 1 minus xt. 2 was there previously. I add minus 2.5 to it. And then on solving further, we get the value as this. Now we can say that h1t will be 1 if the entire term is above 0.5 and 0 otherwise. So this is just an enhancement of the step activation function usage, which we have done previously in the ANN video playlist. I just use the concept over here, but I used it for a different purpose to tune the parameter b. And the term -1, 1, -1, usually you can find it using the ways it is mentioned in the part 1 of the video playlist of ANN, where we have nodes like this. We create a complete node architecture and then say that 1 or -1 is okay or not. We create an entire table of w1 x1 plus w2 x2 and so on. We can proceed in that way, but since it will be a time consuming thing and the data set is finite and we have a lot of other things to cover, it will be better if we proceed heuristically and find out the result as I am doing over here. So we proceed in the same way, and I will definitely urge you to repeat the calculations from your end as well, because this is a very calculation heavy problem, and it's better to keep the PDF open while understanding the problem which I am explaining over here, for just to make sure that nothing gets skipped. So now we proceed further to calculate the H2T. I calculate the same matrix as we did previously over here, and this is the matrix which I am getting. I use the same intuition step I did previously, and I set up, so as of now, minus h1t minus 1, h2 with positive sign, minus xt plus 2 minus v. Ideally the same activation which I used in the previous step is coming handy over here. So just we will plug and play the values, and then we can get the value of b as something greater than 1, and we select b as 1.5. Now we have a lot of recurrence equation available with us. So let's proceed with the one which we first established. So we said that yt is the step activation function of h1t, h2t plus 0.5, which will mean that yt will be 1 if this entire term is greater than 0 and 0 otherwise. We can write it in the vector notation and say that this is v, and this is the hidden state. Now if we recall the lecture which we did previously, part 1, we can say that we definitely needed a matrix v to map the hidden state st to the output. This is exactly what is being done over here, just that over there we had an activation function g, but we don't need that sort of activation function over here. We just needed a step activation function, because first of all data was limited, and the problem statement was pretty simple to be solved numerically. But in real sense we will definitely need activations like tan hyperbolic, sigmoid, or softmax. But as of now, this is how the V looks like. Just remember the dimension of V, which was set up to be P cross M. P was like the number of feature values corresponding to YT, which is 1 over here, and M is the number of hidden states. Hidden state was 2, like we had H1 and H2 over here, and ST is also H1 and H2, and B is just a bias term which we are considering. And on simplifying further, this is what we are getting. So this is the last step of our RNN functionality, where we used to say that YT is a function of V of ST plus C. So C is taken up by minus of by, ST is taken up by HT, and V remains as it is, and this function F is taken up as a step activation function. Now there used to be another step which was like, we have U, we multiply with xt, we have W with multiply with st minus 1, we add B to it, and there is another activation function G which will be like equal to st. Just that the st and ht are used interchangeably over here, and we will combine the two activation functions h1t and h2t, which we determined in the previous step, to write the entire formula over here. So we can say that if h1t is supposed to look like this and h2t is supposed to look like this, our u could easily be minus 1 comma 1, which is coming from here, right? And from here it will be like minus 1 comma 1 again. So this completes our U matrix, and since we have something to be multiplied with xt, oh sorry, this is my W matrix I should say, since we have to multiply a U matrix with xt as well, so the coefficient of xt will become the U matrix minus 1 and minus 1 in both the cases. Like over here it was minus 1 for h1t, and for h2t we have minus 1 again, and the bias term remains like the value B. It is decomposed in the form of two vectors, which is minus 0.5 and 0.5. On solving further, this is exactly how the value are going to look like, and this is the final step which we are getting. So this is what has happened till now. We were given an input value which is x, and then xt I should say, x, then we were able to determine the hidden state corresponding to the xt values, and corresponding to the hidden state we were able to map the hidden state to the output values. Now just go to the question which was mentioned over here, and if we see the architecture, we were able to get the value of u was minus 1 comma minus 1, which was needed. W was also determined minus 1 1 minus 1 1. I hope so this is the right one. If let me check. Yeah, so W is also determined. The value of V was also determined as minus 1 comma minus 1, I guess. The one which we just, yeah, 1 comma minus 1. So V was also determined over here, 1 comma minus 1, and the bias terms remain the same, which we calculated, and these were the activation functions which were needed to be present for us to model the entire step. And this is how we were able to map a given set of input output combination to a formulation of a recurrent neural network. So an input and output combination was given, xt and yt, and we had to like formulate it in the form of an RNN which is supposed to look like that. We proceeded with first of all finding the states which were defined over here. Then corresponding to the states we assigned some hidden weights which were randomly assigned, and in Keras and otherwise it is done with initializers. And then we proceeded forward with finding the first equation from the back, which was like identifying the relationship between yt and the hidden states, like the output and the hidden states. And on doing so we were able to find the value of vector v, which was like clearly showing the relationship between where is it, so which was clearly showing the relationship between the ht's and y's. Now since we were able to get the relationship between the hidden state at time t and the output state, we proceeded further to establish the relationship between the hidden state at time t with the hidden state at time t minus 1, and then once we were able to do that, we got the final result as we needed. So it was quite a lengthy example where a lot of calculations went in. I will urge you to do it step by step again from your end to get the better understanding of how the parity bit problem works. And we will solve a similar problem in the next video as well, where it is more of a problem where the initial state estimation is not supposed to be done. So that's it from this video. Thanks for your time.